Hi everybody, my name's Gwyllim Jahn. I'm going to be presenting some of the work that we've been doing at Fologram, which is a tech startup based here in Melbourne that builds mixed reality software for fabrication and craft. I started the company along with Cam Newnham, who is another RMIT alumni, and Nick Vandenberg. In this talk, I'll try to outline some of the goals that we have at Fologram, explain how mixed reality fabrication is different, I think, to other forms of digital fabrication and pure analog handcraft, and present several case study projects to try to illustrate some of the benefits of mixed reality fabrication for designers and makers. Our work at Fologram aims to extend the limits of what we can build and thereby enable more expressive design. My background is in architecture and design, and we actually built Fologram originally as a sort of a toolkit because we were trying to solve our own problems. We were designing forms which were difficult to fabricate either through robotic fabrication processes or by conventional means like drawings and 2D instructions and templates and things like that. And we were frustrated by that kind of constraint on how we could sort of materialize our designs. What Fologram has grown into as a design practice is a sort of an exploration of some of the implications for the new capacity to build things in mixed reality on design and on architecture. So a lot of this presentation is really going to be about me talking through what sort of forms of design mixed reality enables and how you can design through some of the both opportunities and also constraints and limitations of mixed reality fabrication. We work primarily with mixed reality to display fabrication instructions in the form of sequences of what I'll call virtual templates, which are just exactly the same as physical templates, but they don't exist in the physical world, they exist in the virtual world. Forming and assembling materials from mixed reality templates combines the adaptability of handmaking with the precision of digital modeling, and there are sort of unique capabilities and affordances beyond analog craft or computer-aided manufacturing alone, I think. What makes it unique is that mixed reality fabrication allows for subjective design decisions to occur in response to digital information. And in turn, this allows craftspeople or designer makers to continue designing all the way through the process of actually fabricating and making something. And then this, in turn, enables improvisation in response to complex problems that would be extremely difficult to encode and automate, and for building complex designs that would be ordinarily very difficult to draw. So digital design processes can leverage traditional craft and produce strange hybrids of the two. And that's the sort of opportunity for designers and architects who are intending to materialize their designs in this way. The idea of craft and construction processes that embrace adaptability in designing during making is something that was quite prevalent and also necessary during the construction of Gothic cathedrals, like 1,000 years ago, because of the wide tolerances that you would expect to find on construction sites and because of the lack of notational drawings. So Gothic buildings were still built from drawings, but those drawings are often done at one-to-one scale on the floor of various kind of template houses for building the parts of the building, or they might have been done at one-to-one scale on site, or drawings might have been little sketches to communicate sort of rules of thumb and know-how and things like that. But with the invention of notational drawings during the Renaissance, what happened is that architects came to sort of take total control over every detail of a building before it was built, rather than drawings being produced during construction. Drawings were produced before construction. Every aspect of the building and design was explicitly kind of detailed and documented and dimensioned. And the idea of leaving design decisions up to fabricators during construction became kind of anathema to architects, because you wouldn't be able to control that. You would no longer be delivering your masterful idea. You would be delivering something which was out of your hands. And that came with a certain amount of risk. And architects don't like risk. And since then, so since the Renaissance, the history of design and construction technology can be understood generally as the sort of continuous application of technology to replace this risk of skilled manual labor with the certainty of automated machines, standardized materials, and repeatable processes. Fologram instead aims to expand and enhance manual labor through technology. And so this is a sort of polemical position that we take, I guess, on what technology should actually be for when it comes to the design and construction industries. We are interested in imagining this kind of alternative relationship between designer and the thing that gets built. So rather than the image we see here on screen, which is a vision of the future from about 100 years ago, in which the architect is sitting in his little box and controlling every aspect of the construction process through these sort of mechanized arms, we're instead interested in improving the interface between the architect and a craftsperson, rather than between the architect and these sorts of machines. We're interested in what a new form of Gothic architecture might look like, one that's facilitated by current generation craft that has been sort of accelerated and guided through these new kind of mixed reality technologies. Fologram provides this guidance, or this interface, by replacing 2D drawings and projections with immersive and contextual 3D environments, and this has implications for both designers and fabricators. So for fabricators, mixed reality enables digital fabrication using existing analog skills and tools. This is really important because if you want to get any kind of skilled craftsperson or trade to work with a new technology, you don't want to replace all of their existing skills. You don't want them to have to go back to square one and start to learn how to do something in a new, different way in order to get any benefits. Instead, what you want is you want them to be able to take all of their existing skills as a foundation and then extend that to enable them to do more. So in this video, this is filmed through a HoloLens headset, and you can see this bricklayer, he's templating things out from virtual bricks, and he's able to still catch rulers and things like that and chat on his phone. All of these kind of normal ways of working, normal processes, they stay the same, but you have access to this reliable, precise digital model showing you where each brick needs to go. For designers, the new capacity to build from digital sketches decouples design complexity from documentation complexity. So ordinarily, if you introduce variation into a design, so a lot of modern architecture is made up of grids and repeated elements because of the efficiencies that you get from both building and documenting that. It's also that kind of stems from a shift from one-off bespoke ways of building components to industrialized manufacturing through things like casting processes, which just innately produced like copies of objects. So there's a sort of like inherent cost because of our systems of production to introducing variation, and that is one of the things which has led to this sort of excitement by architects over the last sort of 30, 40 years in computer-aided manufacturing, because with things like robotic fabrication, CNC processes, it is possible to get 3D printing to introduce variation in design at no additional cost. However, those digital fabrication processes and also conventional documentation processes, they do come still with the cost of, whenever you introduce more variation and complexity into a design, it typically still requires more documentation. That's not the case with mixed reality, because you're able to build purely from a sketch. So anything that you can draw on the computer, you can see in mixed reality, and then depending on how skilled you are and how tolerant that design is of deviation from that digital model, it can be used as a guide for fabrication. And this is like a pretty exciting implication. Because design models viewed in mixed reality are explicit descriptions of design intention, explicit description of fabrication information is often unnecessary, as this information can be implied from the design model alone. So we call this, when you imply how to build something from the design model, we call that implicit fabrication. Implicit fabrication exchanges exactness and repeatability, things that you might get with digital fabrication, for speed and adaptability, which you don't necessarily get with digital fabrication. I'm thinking mostly about, say, 3D printing at the moment. When you 3D print something, if that print fails halfway through the print because, say, your material slumps and behaves in an unpredictable way, print might subsequently fail. Often there isn't really a way to adapt to that failure other than to go back to the digital model, change the digital model, regenerate all of your code for creating the print, run the print again. By contrast, in mixed reality, you're able to improvise while you're fabricating things, and that gives you adaptability. You are still a person with agency. You can decide how you want to act and follow instructions, and that gives you this flexibility to react to material while you're forming it. A project for a bent steel chaise lounge provides a kind of archetypal example of implicit fabrication. This is a digital model for the chaise lounge. It's sketched in 3D in Rhino using nothing but a fairly arbitrary collection of polyline geometry that's not rationalized in any way whatsoever. The design contains intersecting parts, physically impossible geometry, no labels, no repeating dimensions, and no 2D drawings. The chair can then be fabricated in under 7 hours by viewing this digital model at full scale and precisely located within the context of the fabrication environment. This allows fabricators to imply the design intent from the sketch of the digital model and permits precise adherence to the design model where that's required and approximate adherence where it's not. Enabling fabricators to improvise solutions to unplanned design challenges while still regulating the work to match design intent makes implicit fabrication robust and resilient to cumulative errors regardless of the complexity of the design. And so while I flick between these two images, if you look at any one part of the image, you'll notice that what has been built is slightly different to what was in the digital sketch. But that's also partly because I'm trying to match camera angles here between the view in Rhino and the photo of the chair, but it's also because the sketch is never intended to be followed perfectly, and it in fact can't be followed perfectly because it doesn't actually follow the rules of the physical world. You have to deviate from it to build it, and the idea is to convey instead the design intent, and the design intent stays the same. These two objects, they look pretty similar in terms of their language, their scale, their function. Very similar techniques were used by FabPub to build the skin of the whale shark for the FIFA World Cup in Lusail in Qatar, which, as far as we know, is the largest structure built using mixed reality. And this structure was built with similar techniques where you're trying to fabricate something just precisely enough to match design intent rather than extremely precisely in order to build it very, very quickly and efficiently. Unfortunately, we can't claim to have invented the idea of using mixed reality or augmented reality, I'll use those two terms interchangeably, for fabrication or for making things. That isn't 100% our idea. And in fact, the opposite is true. So the term augmented reality was first kind of invented and used by two engineers at Boeing in the early 1990s to describe a system for helping with the manufacturing of aircraft wings. So ever since the conception of the term augmented reality, it was designed or intended to be used to help with making, complex making in particular. Whereas now AR is sort of more commonly associated with Snapchat filters or games like Pokemon Go, or even just, selling products online and things like that. That definitely hasn't always been the case. And one of the kind of primary predicted benefits or use cases for augmented reality was fabrication. But we haven't seen broad adoption of AR for fabrication, mostly just because the hardware hasn't been good enough, but also because architects aren't actually designing for the capabilities of mixed reality fabrication. So around the same time that engineers at Boeing were coming up with this word, AR, researchers at Columbia University were also using AR for construction. Architects are really great at adapting new technologies as soon as they come out. Like right now, architects are going gaga for AI and things like that. And it makes sense because challenges in construction are similar to challenges in aircraft manufacturing. Like buildings are kind of one-offs. Aircraft are limited run, large-scale kind of vehicles. They're both big, they're both complex, they involve lots and lots of systems. It makes sense to use AR for both of them. However, conventional buildings are already highly optimized for conventional construction. And so back in the 1990s, and actually until sort of the release of the HoloLens in 2016, mixed reality systems struggled to demonstrate large productivity improvements over other methods, like conventional drawings, physical templates, CNC manufacturing. And so because they couldn't demonstrate big productivity gains in conventional construction, it was hard to justify the costs of implementing significant changes in how we would deliver buildings in order to use AR at all. And as I mentioned before, because of that, there's very few practical examples of mixed reality fabrication to be found in creative practice or in academic literature, primarily just due to these sort of technical barriers to adoption. It's hard to get AR to be more efficient, more precise than other ways of building things. And in fact, this is a fairly exhaustive list of any mixed reality fabrication done since the invention of the technology. Some of these projects are really amazing, in particular work out of Tokyo by Yoshida doing chopstick assembly in 2014. That was a really innovative project because that really was looking at some of the kind of unique capacities of mixed reality fabrication, but most of and similarly actually doing some brick stacking in 2017. But most of these other projects, they all actually took place after we started doing things at Fologram, or they were looking really at mostly precise fabrication, where you're just trying to, as faithfully as possible, duplicate a digital model. And when you're looking at precise fabrication, so examples would be these sort of sculpting applications or painting applications here. In these systems, what AR does is it basically tries to guide human labor to the extent that it's just automated. So there's not really any capacity to improvise with these systems. You're being told exactly where to carve material or exactly where to paint things. And that then prohibits any sort of improvisation or design changes during making. And in turn, I think that kind of fundamentally misses one of the big opportunities of AR fabrication. That's kind of the case with all of these projects except for the one by Yoshida, the chopstick pavilion. So another reason that mixed reality fabrication was largely underexplored is that most researchers that experimented with mixed reality mostly focused on assembly tasks in which the thing that was actually being assembled, like the designs they were trying to build, was usually quite arbitrary. It was almost like a control that was necessary to the point that it could be used to compare assembly time and mistakes to alternative approaches. Again, AR was just trying to be used to make assembly faster and more efficient. And that is that, like, these researchers, they didn't really think about how making in mixed reality might impact the space of possible things that could actually be made. So something that our work at Fologram does differently is that rather than treating design as an arbitrary control and just trying to build that design faster, we're considering how to design for the unique affordances of mixed reality fabrication. We're really, really interested in discovering whether or not mixed reality enables design that could not be built in any other way. Our design agenda at Fologram has engaged with aesthetic frameworks that lie between robotic precision, handcraft, and volatile material behavior. And typically we try to resist the urge to impose top-down design intent on the things that we are designing in favor of kind of simulated material behaviors and complex emergent phenomena. This design agenda makes us like uniquely positioned to benefit from what you can do with mixed reality fabrication and handcraft. And it's influenced by a very small niche within a community of designers engaging, for the most part, with robotics in architecture, new materialism and digital craft. And a lot of these practitioners have at some point come and run studios at RMIT. So we were engaging with this agenda prior to the release of the HoloLens 1 through like design studios and speculative architectural competition work. And mostly we were trying to materialize the things that we were designing through autonomous robotic fabrication systems. So before I jump in and show you some of the design projects we've done at Fologram with mixed reality, I'll show one project just to give this a little bit of context. And this is a project for a RMIT meeting room called the DAB Pod. The DAB Pod is designed for a pavilion from an aggregation of recycled plastic bubbles. It's basically looking at, like, can you create some of the effects of blown glass, but from recycled plastic to reduce the cost and fabrication complexity and things like that. It's interested in exploring the variable effects that are produced when working with the volatility of moldless inflation and how these effects can be distributed and controlled using algorithmic design and fabrication processes. It was really just following a hunch that there existed a set of architectural effects that are underexplored just because they're difficult to build by hand and they're difficult to automate. Together with Cam Newnham and Roland Snooks, we spent about a year developing systems for controlling robots autonomously in real time to be able to actually build those kinds of designs I was showing in those previous images. So rather than sending a toolpath to the robot and having that run until finished, the target point of the robot would be continuously streamed from design software, and that would then allow for the motion of the robot and any extruder which was attached to it to be controlled algorithmically in response to scans of the material. The idea is that you could make really simple changes to the placement of material with a robot, observe how the material behaved, and then react to that in the manner of a craftsperson. Like, albeit a very kind of unskilled, rudimentary craftsperson, but you would still have some feedback there. And our hypothesis is that this would lead to emergent effects and would also lead to being able to build things without molds. So that video I showed just a second ago was a prototype of that real-time robotic system working with extruded expanding foam. But that was a stand-in for inflated plastic once we had the means of working with that material. And the means of working with it was achieved through designing and building our own custom plastic extruder. This was way back in 2015 or 2016. And like now RMIT has much better extruders. But this is a small extruder that could go on the end of a UR10 robot that you could easily stream toolpath positions to. And we also made a custom extruder because we wanted to be able to put a custom die on the end of it. So together with, at the time, a student of mine, James Pazzi, we designed and fabricated this extruder and a tube die, which you can see down the bottom of the screen. Here, I think my face is probably covering the image of the die itself. And the tube die would allow us to extrude plastic in the profile of a tube and blow air into that tube using a digital pressure regulator that we could control parametrically in Grasshopper. So you'd have a slider in Grasshopper that you would drag, change the amount of pressure that's being blown into this tube, and inflate the tube as if it was a plastic bubble. And this is the first test of that. We're just extruding without moving the robot, blowing up these plastic bubbles. Small prototypes produced with this extruder demonstrate what's essentially a method for 3D printing with bubbles. And bubble prints are a really fast way of making like large volumes at the cost of not being that precise or repeatable. The autonomous deposition of these bubbles or foam does have a lot of the qualities of craft. It's kind of a negotiation between form, tool, and material. And these qualities are sort of, you could almost think of them as discovered material effects, or material effects that emerge through allowing material to take on form that it just wants to take during the process of crafting it, rather than just forcing form into material, which is what a lot of digital fabrication processes and modernist processes have done since the Industrial Revolution. And so these qualities, they're sort of desirable maybe because right now they're a little bit unfamiliar, because this way of producing buildings and objects has been lost in favor of kind of standardized, repeatable processes. However, I think that when you try to encode craft processes into automated machines, like we did with this project, it's a little bit problematic still. And the reason for that is that it shifts the interface between the designer and materialization from a sort of social interface, like you'd have with traditional craft, which would be expressed through people and language. Like if you actually had artisan craftsperson blowing glass and you were trying to describe and communicate to them what you wanted to build, you would do sketches, you would talk through the qualities you wanted, you would learn from what that craftsperson could achieve. You'd kind of work through something in quite a social way, let's say. Rather than materializing craft like that, instead the interface becomes more of a technical one, which is expressed through machines and code. As in, we're expressing the qualities of craft through things like the degree to which we can scan material and identify forms in that 3D scan, and then control where we want the robot to move to, and then decide how much to change that slider in Grasshopper to change the pressure in the tube. All of that becomes extremely technical, and this makes technicians the producers of craft knowledge and designers the consumers of this knowledge, removed from the practice and tradition of craft through these sort of black boxed layers of technical abstraction. It becomes harder and harder and harder to share that technical knowledge with anybody who isn't technical themselves. And I think that's sort of a problem, because craft traditions are things which are sort of valuable just because they've been sustained over such a long time. And they're sustained and they gradually evolve. And that's what makes them valuable and interesting. And I think it's problematic to translate that knowledge into a kind of a different domain that prevents those traditions from continuing. So all of the material effects of the DABPod project could be achieved by working by hand in mixed reality while reducing the technical overheads and digital documentation required to do so. It's just that when we designed the DABPod, the HoloLens didn't exist, and so we didn't even consider it. But in 2016, just after we finished making that extruder, the HoloLens was released. RMIT had a couple of headsets sitting around. Cam and I learned that they existed. We tried them out. And the second we tried them out, we knew there was an opportunity to use them for fabrication, even though they weren't that precise. And so we first tried fabricating something with the HoloLens. This is a video of the very first thing we ever did at the end of 2016 with a aggregation of pebbles. We modeled a really simple curved surface, used that as a guide for where to place pebbles. At first we were just trying to place it looking at the whole surface at once, and then we thought it'd be easier to split it up into kind of contours. And we demonstrated within a couple of hours that this idea of like making things from holographic guides or virtual templates using the HoloLens was definitely possible. Because of our interest in very wide tolerance design, volatile material effects, and the relationship between digital modeling and handcraft, this first Pebble project seemed like a really massive success to me, while for other researchers, designers who would have been interested in sort of optimizing and improving the performance of more conventional, like of fabrication, more conventional designs, this pebble making process might have instead seemed like a massive failure just because it wasn't very precise. So because I wasn't that interested in precision, this seemed like a huge opportunity to do something with mixed reality for craft. So we then, at the end of 2017, we started Fologram as a company so that we could support the development of this software and get it into the hands of more people. That's what we still do. So we at the company develop integrations for Rhino and for Revit that create real-time connections between CAD and the HoloLens or other mixed reality devices. And how Fologram works is, generally speaking, what you're doing is you're locating a digital model, which exists in, say, Rhino or in Grasshopper, in physical space, using some QR code markers to make that location very, very precise. Then we can stream geometry from Rhino and Grasshopper. So if we change something in our parametric model, like drag a slider, we'll see that geometry update immediately on the headset. And lastly, we can interact with that geometry on the headset. So we can press on things or pick it up and move it around. And we can detect those interactions in Rhino and Grasshopper and update our models, send the geometry which has been changed back to the headset, and it'll be as if we're interacting with like quite powerful applications, even though Grasshopper is handling all of that application logic. So that's how Fologram works. And you can use Fologram to do some pretty strange things. So the first time you view a model in mixed reality, you often want to pick up a virtual model and move it around, and then you probably want to throw it. And you can build apps in Grasshopper where you can basically detect the direction that someone's hand's moving on the HoloLens, and then use that direction to move an object over time in that direction with a sort of a parabolic path. And then you can use that to make darts games. So it's like what Fologram does is it lets us think about design software and what it's for differently, because we use that software in a completely different context. So rather than being this interacting with that software through a 2D screen and the interface of a keyboard and a mouse, you can interact with your design models through the interface of your hands and your body, and then in the environment of a three-dimensional space. And that is, pretty exciting in terms of unlocking kind of new ways of building apps and design tools. However, primarily we're obviously interested in handcraft and mixed reality. Handcraft and mixed reality is, generally speaking, a kind of a reaction to the aesthetics of mass customization and robotic automation. I've already mentioned that implicitly before in sort of some of our work and projects. And they themselves are a reaction to the smooth curvature and splines that characterize the first digital turn. So a lot of my work designing for mixed reality fabrication is sort of looks smooth and curvy because, not because of a nostalgia for this period of digital experimentation driven by the affordances of animation software, but instead, like I'm about to show a few projects which they're more entrenched in a nostalgia for architecture that predates notational drawings and was instead driven by the qualities of craft and the idea of designing and making through templates rather than drawings. In other words, a lot of the projects I'm about to show, they're curvy for some of the same reasons that Gothic buildings were curvy, rather than being curvy because that's how like Pixar animation software lets you model organic characters really easily. So I'm going to now jump into a couple of projects to illustrate this for the next half hour or so. Specifically, what I'd like to do with these projects is talk about how I or we at Fologram design through the affordances and limitations of making things in mixed reality. And mixed reality fabrication enables quite a broad spectrum of different approaches to this. So we can represent fabrication information both abstractly and approximately, like with the chaise lounge, or represent it very explicitly and directly, so that somebody could make something quite precisely in mixed reality. The precision or the expected, like almost like the tolerances of the produced object can be very wide and very rough, which leads to a certain kind of aesthetic, or it can be very exact, which leads to an aesthetic which is more similar to, say, other forms of digital fabrication, because you're producing what's close to a copy of your digital model. And then we also have certain degrees of like directional guidance in mixed reality as well, where you can allow, or you can work from digital models which are just static or passive, or you can work from interactive digital models which are constantly, say, scanning the material you're working with and changing the instructions that they're giving you in order to guide you towards a particular outcome. So I'll try and illustrate all of these different spectrums through several projects. These projects occur over a timeline of the last sort of six years or so. And again, I'll focus on projects which are like mostly because they're different to one another. There's a lot more projects that we've done, and you can find a lot of these on our website if you're interested in them. Okay, the first project that I'll show is called the Woven Steel Pavilion. And this is a project that we did in 2018 for a workshop at Cadrea in Beijing. And they explore how the ability to fabricate digital models roughly and quickly impacts design. In these projects, we were designing larger scale structures from hand-bent steel that necessitated being quite explicit, or relatively explicit, due to the inability to form larger scale material like approximately with bench-mounted tools. And we were trying to explore design conventions in mixed reality as well. We were sort of trying to think through what sorts of rules you should follow when you're designing for mixed reality. And these rules we were starting to work out involved things like not designing parts which were repeating, because repeating parts you would notice that each part was slightly different because of the imprecision of the fabrication process. We were designing parts which were largely flowing through fields, because that flow led to a legibility of the consistency of the whole, rather than, again, you noticing the imprecision of any like one individual part or joint. It's almost like coming up with techniques for blurring or hiding the fact that we're making these structures like fairly approximately. So we ended up with a design like this, consists of a ton of interwoven parts. And the reason for this is, despite its complexity, the design is actually quite tolerant of error and deviation. And this is because if you fabricate one part incorrectly, because the material is still a little bit flexible, it can typically be made up for by an equal and opposite bend in another part during assembly. And so any small like errors and changes can be accommodated for. So I'll show you how we made it. The project was deliberately very low tech and very, very low cost. So we took a cheap bar bender that we bought in Australia, or tube bender, and we welded that bender onto a column at the architecture school, and then overlaid a digital model of how to fabricate each part over that bender so that you could use it as a kind of interactive guide during fabrication. So this improves the skill and capacity of fabricators to work with complex spatial instructions by reducing the dimensionality of a task to just a single bend plane. You take your pipe, put it in the bender, align it with the start of the bend, which is what we see here. Once it's all aligned, then you just bend it around using that tool, which only bends in one plane anyway, until your physical part matches the end of the bend, and then you know that it's right. So the fabricator could then infer like the length, rotation, and bend angle for each segment in the part geometry from the virtual model, rather than any of this needing to be explicitly dimensioned. So you're never showing like the angle in degrees or the length of each segment of the part, partly because that just leads to human error. You're just representing everything visually. The assembly of the project existed in a kind of quantum state where the parts of the structure could be simultaneously wrong and right. So we have these fabrication processes where we can partly install parts and then go and correct the position of the part later on. And that now allows for kind of a non-linear assembly sequence without complex documentation. So you're kind of weaving a part into the structure, temporarily fixing it in place. It's flopping into like the wrong shape. But because you have a hologram showing you exactly how to install that part and all subsequent parts, you can always adapt it and change it later. This enables improvisation in how the structure is assembled, and you're always adding the easiest part to install based on the contingencies on site rather than needing to anticipate this in the digital model prior to construction. Fabricators can also improvise how to weave the parts into the structure like you see here. This is something that's really intuitive for people but extremely challenging to automate with path planning algorithms with robots. We also had a really simple interactive model for viewing parts in mixed reality. The idea here is just to reduce the cognitive load of switching between the task of physically installing a part and the abstract task of figuring out where a part should go, which would typically be done by reading drawings. It also makes it super easy to perform basic quality control because you can see if a part has been fabricated incorrectly while you're assembling it and just get it to be remade if you had to. So even though we're performing parts approximately with a manual bar bender, and these are being installed in an improvised way, the tolerances in this approach still aren't too bad because of some flexibility in the material. So fabricators are able to improvise how to deform parts during assembly in order to best match the digital model. And the result of this is that after we digitized the structure, we found that there's only a relatively small average deviation of about 16 mil from the digital design model, with a maximum deviation of 46 mil. So this is the original digital model, and that is the as-built model. So much like the chair, you can see that these two things are slightly different. Again, max deviation of 46, average of 16 mil. But the design qualities are exactly the same, and that deviation is like well within our assembly tolerances. So given that we fabricated this structure or that chunk which was digitized in half a day, we thought that those tolerances were acceptable. And we've done a bunch of other bar bending projects like this. This was one that was completed at Robotic at ETH in Zurich later on that year. The next project that I'll show is called Barkitecture. And with Barkitecture, what we're doing is we're making the joints between... In the woven steel pavilion, we were making the parts quite precisely because we're explicitly documenting the exact bend angle of each one of those parts and then trying to match that as accurately as possible. And then in the assembly model, we were showing where the parts would go, but there was a lot of tolerance in how they were assembled together. You could have tolerance in the joints and flexibility in the material, and you would kind of get a reduction in accumulative error because of that flexibility. With the next project, we do the opposite. So we very approximately form parts with very flexible material, but we have extremely precise joints. And so the idea is that you form parts into rough shapes just to get them to be slightly easier to assemble and place roughly in the right place. And then when you rivet the joints together, the whole structure pulls itself together into an exact shape, which has very low tolerance. So the joints themselves have almost no tolerance, and this allows you to fabricate very complex structures very, very precisely. So we're increasing the precision here. This is a little video of that project. Talks you through the process. The project was completed at in a 2.5 day workshop at Acadia at University of Pennsylvania. 400 parts, 1,500 rivets. formed from 25mm aluminium strip, which is a really cheap material. So this is marking out those riveted joints between the parts. And because this is a 2D templating process at relatively small scale, this is very accurate. You can mark those parts, those joints, to within a millimeter or so. Then you cut the part to length, drill out all of the holes, and now assembling the part would be tricky as a straight piece, so you form it into roughly the right shape just by hand. So it's placed in a vise, and then it's aluminium, so it's sort of plastic, and plastically form it into roughly the right shape. But the tolerances here are really wide, so this is maybe within sort of 25, 30, 40 millimeters of the geometry of the part, but still very flexible. And then once you have that part formed, you can locate it in a structure. And here the assembly information, or the complexity of the structures, would be almost impossible to communicate with drawings. It's really, really hard because the parts aren't perfectly accurate. It's really hard to tell which part should connect to which joint. And so we have a digital model here which is trying to communicate that as best we can, describe the topology of these sort of woven structures. And so long as that model in mixed reality is accurate enough to tell you which joints to connect, once you've fixed those physical joints together, it dials that precision right in because the parts are self-registering. And then there's just a couple of videos. In all these workshops, you always end up carrying these structures from one part of an architecture school to another. And that's the completed thing. Another pavilion that I'll show you just before we jumped into some more serious projects. This one works with similar logic, or at least logic for making the structure as those previous two projects. So it's a bunch of very thin 6mm aluminium rods that are bent using the exact same technique as the woven steel pavilion into frames. But these frames form closed cells so that you can apply heat shrink wrap to those closed cells and fabricate a surface geometry. So this project was completed with RMIT students during a summer studio at the start of 2023. So it was a 4-week project. And this shows a lot of those frames that are being clad in this heat shrink polyolefin film. And these produce these sorts of, I called them 3D canvases. So they're not flat canvases, they're double curved canvases that would be difficult to project onto. And so what we were doing is with the HoloLens, we were showing a 3-dimensional image which wraps and fits perfectly on those 3-dimensional canvases, which is almost like a paint by numbers instruction set that let us then go and apply patterns and images and ornamentation to these surfaces, which we would hand paint on. And because of the material is quite delicate and the geometry is like highly variable, this would again be difficult to automate and difficult to do with any kind of conventional documentation techniques. And so it's a new affordance of mixed reality, which is why I show it here. We've done some other projects. This is one that was a shorter workshop at Bond University. The next project that I'll talk about demonstrates quite a different approach to mixed reality fabrication, one in which the forming process is very much guided through computer vision and algorithmic processes. So rather than working from a static 2D virtual template, as in most of those other projects I've just shown you, you're instead working from a dynamic template which changes color to help inform you about how precise a particular fabrication project is. So this is a project a little prototype that we did in our office for exploring how complex double curved surfaces could be assembled from lightweight, flexible materials without any underlying substructure. And so we're just using office paper here, printer paper, because that's all we actually had in our office as a material at the time. What we're doing what you see in this video is what we were actually seeing through the HoloLens. So these double curved surfaces were built from paper strips without any formwork by comparing a real-time depth scan. There's a scanner in the HoloLens 2 of the as-built form of the paper with the like a mesh of the target digital model in Grasshopper. And then feedback could be provided to the fabricators on where the structure deviates from that digital model using color. So when the paper strips are a long way away from the digital mesh, we render them as red. When they're in the right spot, we render them as, I think, green or transparent. And so as you're moving around with your paper strip, you'll see the color change. And when it goes green, you know it's in the right place, and you can sort of try and glue it in there. You can see that strip going red and transparent as Nick's moving it around in this video. So after we did that prototype, together with students in an elective, again at RMIT, this was in the middle of like a winter elective in 2022, we explored how this approach could be scaled up into more permanent, larger scale objects using eucalyptus and paper bark. So what we did is the students modeled simple sub-D surfaces to define design intent, and then these were the only design information used to fabricate. The idea was we would make these 8 kind of monolithic objects which would then fit together to form a large kind of partition wall in our office. And they'd use depth feedback to guide how closely the bark matched that surface. And we were using paper bark because that was a material that was readily available for free, and a material that isn't commonly used in fabrication. So you can find paper bark all over Melbourne. There's so many trees that you don't have to harm any one tree. You can kind of take the bark that's basically falling off the tree. And it has this really beautiful gradient, a set of gradient qualities, like changes in color from like really light to really dark, changes in texture, changes in the thickness, and therefore like the kind of flexibility of the bark. And these all become, and even some bark has these kinds of streaks through it. These all become design parameters which would be really hard to work with in your digital model, but are really easy to improvise with from available materials while you're forming something. So paper bark was free. It had this really diverse set of qualities, but it's hard to work with because it's hard to digitally model those qualities. The material is like very heterogeneous. It's not like an engineered material that's predictable. So we treated that as an opportunity rather than as a constraint. And what I really like about the objects that were produced with this material and this technique is, I mean, they're much better than the paper objects, I think, because they have they combine the qualities of the digital modeling software with the qualities of this physical material. They have a kind of a strange sort of otherness to them that is both, you can kind of recognize some of the Rhino sub-D model in it, but they also, look a bit like trees, obviously. And they also capture kind of the skill that the students developed in how they would kind of apply this bark and let the direction of these strips of bark flow over the surfaces and change the color of the bark and all this stuff, which is really associated just purely with craft. So what I think is particularly kind of I think this approach to working with mixed reality that enables you to work with materials that would otherwise be overlooked is super valuable, especially working with, say, like natural materials or non-engineered materials or recycled and reclaimed materials. And I'll show another project that explores this, like a similar idea, shortly. The next project I'll talk about is a project called the Steampunk Pavilion. This was a project that was designed by myself and Cam Newnham, along with Igor Pantic and Sumin Ham, with engineering by Format Engineers. I think that this project hopefully is, again, it's like a complementary approach to the previous two. We've seen one project which is about explicitly forming steel parts into a malleable assembly. We've seen a project which is malleably forming flexible parts into an explicit assembly. We've seen a guided approach to fabrication where the parts aren't documented at all with the paperbark project. And in this project, we have a very implicit approach to like approximately forming timber strips, and a really explicit approach to forming quite precise steel brackets. And the combination of the two gives us this kind of just enough control over the precision of quite a large scale structure. The Steampunk Pavilion is interested in exploring how the traditional craft of steam bending can engage and negotiate with the smooth splines that are easily produced with current generation like digital modeling software. And some really early ideas about how mixed reality might make the process of setting out the templates for steam bending more efficient were based around designing an adaptable scaffolding system where you could easily reposition that scaffolding and therefore describe like any three-dimensional curve in our design. Steam bending is very much a craft, and that's partly because it's extremely difficult to model, like digitally model the behavior of timber, because natural, like non-engineered timber has defects, knots, grains, grain run out, things like that in it, that is always like unique to every board of timber, which makes it just very hard to digitally model. You can only approximate it. And so as a result, the technology in craft largely died out with the invention of plywood in the early 1900s, because forming plywood, like glue lamination, things like that, was just much inherently more controllable, precise, repeatable. So this idea of steam bending timber, we tested it with some small prototypes in our studio and proved that the concept worked for like the first stage of the design competition. Our approach to designing something for the competition was really just premised on designing the craziest thing that we could. We were sort of thinking about maybe we could steam bend some kind of timber slinkies to make this sort of superstructure, or maybe we make these timber strips sort of flow through a vector field, really make the form as dynamic as possible. And this was what we ended up submitting for this for the competition. We had no idea how to build it. We just thought that it was like a kind of an evocative form. We'd never done any steam bending before besides that little prototype, so we honestly weren't fully expecting to win the commission. But we did, and so we had to figure out how to build it. The digital model of each timber board was viewed in mixed reality, and then physical formwork for this virtual strip could be improvised, eliminating the need to like predict and model every single bit of formwork for every bit of like timber digitally. Saved heaps of documentation time. And then we used the exact same like bar bending tools as I showed earlier with the woven steel pavilions, with this kind of interactive mixed reality UI for like basically fabricating as precisely as possible a bunch of steel brackets that would pick up on these steam bent boards and allow us to assemble everything into a shell. I mentioned earlier that mixed reality decouples design complexity from fabrication complexity, and this approach to forming the strips, the boards, steam bending the boards, is an example of that. So the only fabrication information that's required was the geometry of the strip. And that came directly from the design model. We didn't have to produce any dimensions, didn't have to produce shop drawings, didn't have to project anything to like construction planes. There's no CNC'd formwork. Even the parts weren't cut into shape. They were all designed from straight lengths of timber and straight lengths of steel. And this gave us massive efficiencies in terms of like the cost of the project and the complexity of all of the documentation. It was pretty necessary to have virtual models on site, just because even though we steam bent these parts to give them a kind of a memory of a particular shape, they would deform under self-weight, and it was easy to elastically bend them out of that remembered shape. So having a mixed reality guide for assembly meant that we were able to kind of weave this flexible material into the target geometry in a process that was much more like building with spaghetti than it was conventional building from materials that are usually rigid. And we could do this without needing to build like formwork and scaffolding on site, which would have basically meant building the pavilion twice, and also without introducing significant cumulative error. All of the steel brackets and timber boards I mentioned earlier, they're all made and designed from linear stock material. So off-the-shelf lengths of 120 mil wide timber, which actually we cut in a mill ourselves, again, to save time and costs. And in order to be formed into three-dimensional curves, these boards and pieces of steel, they need to twist. And the twists mean that the surface of the structure kind of opens up and becomes perforated in some place and aligns to create surface in others. It gives you all of the complex effects of the pavilion. They introduce like another layer of geometric complexity besides just purely flowing parts through a vector field with the digital model, and lead to the apparent randomness of bracket placement, the imperfect differentiation and changes between strip orientations, the occasional kinking or deformation of the non-uniform material, and so on. But I think that these effects don't accumulate to wreck the whole of the pavilion. The whole remains quite consistent, emphasized by the language of the vector field and the sub-D geometry, which are really characteristic of digital modeling software. But all this variation makes the design really difficult to describe with 2D drawing sets, as every single part, bend, joint, and sequence is unique. But it's still relatively easy to simulate in digitally model. And this produces this kind of a combination of like relatively simple 3D modeling with really complex material effects and constraints, which are afforded by handcraft, produce this sort of new architectural expression that we just call roughness. And we call it roughness to contrast with the smoothness of digital modeling, which, you know, we all talk about like smooth blobs in terms of digital models. These aren't smooth blobs, they're rough blobs. The second last project I'll talk about is a series of stacked block structures. These aim to explore how, by designing through the affordances of mixed reality fabrication, we can reveal the capacities of mixed reality to also improve the productivity of conventional construction, to fabricate unconventional designs. So we're sort of coming full circle here, where there's a renewed interest in conventional construction techniques, but not in the assembly of conventional designs like straight walls, planar projections, repeating elements, etc. So again, we've been exploring these structures for a very long time. One of the first things we did with the HoloLens in 2017 was this kind of stacked timber block structure, where we used an explicit representation of the position of every single brick in the design, viewed that in mixed reality, in an attempt to kind of try and improve the precision and repeatability of this as a fabrication technique over the more implicit, approximate approaches that we showed earlier. Like computer-aided manufacturing, variation in parts can be produced with no marginal cost in mixed reality, and all instructions can be generated directly from design models. This represents an accessible and low-cost method for trades and craftspeople to produce the variation commonly generated with parametric modeling software, which we find really exciting. So this is another project, Stacked Block Structures from 2018, done with Art Engineering in Germany. Now we're at sort of 2,500 stacked blocks, just gradually increasing the complexity, or other workshops like this one at USC, where we were trying to increase the scale and exploring whether that would also work in mixed reality. But all of these projects necessitated working with lightweight materials and impermanent structures, just because they were done in these kind of short workshops. And we were interested in how the approach to assembly of like stacked structures would be received by professional bricklayers. So we were given an opportunity to do this with the University of Tasmania in 2018. And so where we were designing, the design actually wasn't completed by us, but we helped a team of bricklayers from Allbrick to build this small feature wall from about 650 bricks, and using a mixed reality guide to show exactly where each of those bricks needed to go. So this is the wall, this is the design model. There's a user interface on the right, up and down buttons to display each course of bricks as it's required, and here's Colin talking about it. Oh, actually, we might not get audio in this recording, but basically what Colin says is every single brick in this wall is in a different position, and it would take a skilled bricklayer about 2 weeks to fabricate normally, but you still wouldn't actually get it that precise just because it'd be so tedious to do all of the measurements for every brick in the wall. By contrast with mixed reality, what we're doing here is, because you can see exactly what the as-built thing is supposed to look like, pretty much anyone can work from it regardless of skill. So they were able to take a first-year apprentice and get him building what would otherwise be a project that requires a super skilled bricklayer, and teach him how to produce like better quality brickwork, because both he and Colin could see exactly where bricks were supposed to go and learn how to make changes to sort of technique and placement and things like that in order to just produce a better outcome, make it more precise, match the digital model. So it's a super effective training tool. The bricklayers also, we found, develop techniques for laying these brick walls in parallel. So normally it'd just be one guy that would fabricate the wall, do all the set out, start from one side of the course, work to the end. But they were able to do it with a team of bricklayers, where one guy would approximately place the bricks and then another guy would come through and adjust it to be really precise, like you see here. So, excuse me, rather than taking 2 weeks to build, this design took just 6 hours to build. And they were really excited about the kind of implications of this approach, because it allowed them to produce a quality of finish that was simply better than what they could produce without using mixed reality. And this is a change for an industry that hasn't really seen any similar impact from any sort of technology since the laser level. The evidence for impact of this in industry is basically the continued and ongoing use. So we've seen mixed reality used for other brickwork projects, like much larger scale benches as part of the Royal Hobart Hospital, or other projects by other architects, again down in Tasmania. So the last project that I'll show is one called the Offcut Pavilion. This was completed for the Building 4.0 CRC conference last year at the end of 2023. And this is a project which is particularly interested in how mixed reality might enable fabrication from waste materials that would be difficult to work with in either automated processes or with conventional documentation. So what we did is we got a whole lot of short lengths of framing timber donated from Holmes Glen TAFE, where they're building roof trusses with carpentry apprentices. And a lot of this material is either warped or contains defects. All of the ends are cut to kind of miscellaneous compound cuts, and so it'd be pretty difficult to work with normally with robotic or CNC processes. You'd have to scan every single length of timber. So instead what we did is we designed a structure consisting of a bunch of short parts and compound cuts on each end of these parts, and we overlaid the mixed reality template for each part on a miter saw, so that you could use the miter saw to set the bevel and miter angles for each cut, as well as template out the joints between parts. And you could improvise which bit of available material would best match the geometry of the part that you're about to cut, and avoid putting joints on knots in the timber and things like that. This system of doing compound cuts from a mixed reality template is really precise, and that's partly because it's fairly small scale, and we used a combination of explicit templates showing the length of parts, say, and actual just like dimensions and notation showing things like the miter and bevel angles that we needed to adjust the saw to. And a combination of those two things made this super precise. Parts were fabricated to within about 2 mil, and then they were installed in the structure using another holographic template. And you can see here the precision of this approach is because that hologram is matching all of the parts. We marked the joint locations, but the parts don't perfectly self-register. There's flexibility in that joint, which gives us a little bit of tolerance during assembly, but could potentially introduce a cumulative error. So by having a mixed reality template for the entire as-built structure, you can be constantly making small changes to how to fit parts together without introducing that accumulative error. So it gives you that adaptability. The parts give you precision, and you also eliminate risk which is one of the first things that I talked about in this presentation. So the intention here is to make an argument that mixed reality enables extremely low cost and very fast approaches to working with zero cost materials with precision that's comparable to CNC approaches if required, and enabling us to produce like double curved complex geometries from framing timber. It's probably one of the most cost effective ways of doing this. So to conclude, why should you be interested in mixed reality and mixed reality fabrication as a designer? I think that there's some opportunities to discover a new architectural style here that couples craft with the precision of the digital. I also think that there's opportunities to find better ways to build in a construction industry that's typically resistant to change. Mixed reality extends the capacity of human labour to produce the subtle variations of digital models beyond what is possible with conventional drawings and tools, and we think that it extends skilled craft. Mixed reality also provides an efficient way to document highly nuanced design intent in a way that workers on site can immediately understand. Hundreds of drawings can be replaced with a single virtual model. The benefit of mixed reality for construction is the capacity to adapt the objectivity of digital models to the messy reality of construction sites, skilled or unskilled handcraft or trades, and non-uniform materials. As hardware gradually becomes ubiquitous, as mixed reality displays become ubiquitous, and we see things like the Apple Vision Pro, demonstrating that more and more of these large tech companies are trying to get into this space, mixed reality will eventually be adopted in conventional construction just because 3D documentation in mixed reality is a more efficient medium for describing 3D design intent than 2D notational drawings. And it reduces the risk of incorrectly inferring spatial variations in 3D form. I think that mixed reality fabrication aesthetically is influenced by the degree to which the work is improvised and how much this improvisation is guided or otherwise informed by virtual models. When virtual models are explicit, the character of mixed reality fabrication resembles other forms of digital craft, and especially if you end up producing what's close to a copy of your digital model, just like a 3D printing process or something like that. I think this is the case with a few of the projects that I showed. Some of these, in particular, things like the clad tensile, like heat shrink wrapped projects, the finished object looks very much like the digital model, and the effects of those projects are designed digitally rather than discovered in the making. However, the capacity to identify and adapt to differences between digital and physical models differentiates mixed reality from other forms of digital fabrication and makes mixed reality fabrication anti-fragile, or in other words, it can benefit from error and mistakes and risk and imprecision and tolerances. This potentially leads to a renewed engagement with non-uniform materials like bark, simply because the complexity and risk of working with them is reduced. And this could lead to a different kind of aesthetic and character of digital objects, things like rough blobs rather than the smooth blobs that we've seen for the past 30 years or so. To conclude, we fundamentally believe mixed reality fabrication should be considered a slow technology, just like the slow food movement and things like that. The act of labouring over materials by hand in mixed reality should not be rationalised through the economics of repeatability and productivity, but instead find value in nourishing craftsmanship, reducing the need for design standardisation, better utilising available materials, or facilitating meaningful creative collaboration. We think that this demonstrates a new approach to thinking about computer-aided design, manufacturing, and the production of architecture. Thank you very much.